Hello and welcome to the chemistry solution. This tutorial is on calorimetry. When we do these calorimetry problems, we're going to make the following assumptions. The first is that our reaction is occurring under completely constant pressure. Q sub P equals the change in heat when a reaction is occurring under completely constant pressure, and that is equal to delta H, or the change in enthalpy. The second is that no heat is being lost to the outside surroundings. And the third is that the specific heat and the density of dilute aqueous solutions are the same as pure water. And we're doing this just to make our calculations a little bit easier. And so we're going to be talking about aqueous calorimetry problems in this tutorial. And in this setup, our aqueous reaction will be inside an insulated container. So you'll have your reactants reacting and either drawing heat from the surrounding water or releasing heat to the surrounding water, which we'll define as our surroundings. So when I say no heat lost to the outside surroundings, I'm talking about outside of our insulated container. It's kind of like we have our system and our surroundings in one container together. And so that any heat absorbed or released in our reaction will be gained or lost from the surrounding solution. And so when we know the temperature change of the solution upon the mixing of our reactants, this allows us to calculate the heat absorbed or released by the reaction. And using this information, along with the moles of reactants, we can calculate a delta H value for the chemical reaction. Let's look at an example. In this example, 25 milliliters of 1 molar NaOH and 25 milliliters of 1 molar HCl are mixed in a calorimeter, and the temperature of the resulting solution increases from 25 degrees Celsius to 28.25 degrees Celsius. Calculate delta H for the reaction in kilojoules per mole. The first thing you need to do when doing one of these problems is to write a balanced chemical equation. And so if you remember how acids and bases react, they always react to form water and a salt. So we have NaOH plus HCl reacting to form H2O and NaCl. Now the notation of AQ in parentheses by the NaOH and HCl means that these are aqueous solutions. So we have sodium hydroxide and HCl in water. So sodium hydroxide and HCl are going to be the molecules doing the reacting, and the water in this system is going to serve as our surroundings. And the water, in this case, is absorbing heat because the temperature of the water is going from 25 degrees Celsius to 28.25 degrees Celsius, and we define the water as our surroundings. Our second step will be to write the amounts and concentrations of each reactant given. So we have 0.5 molar NaOH and 0.5 molar HCl. We also have 25 milliliters of each of these solutions. The third thing that we need to do is to calculate the heat transferred in the reaction. And again, we're going to assume the specific heat and density of pure water. In order to calculate the heat transferred, we'll use the equation that the heat, Q, is equal to the specific heat times the mass times the change in temperature. So the specific heat is the same as that of pure water, 4.18 joules per gram degree Celsius. We multiply this times the mass. But you're probably looking at your problem and wondering where the mass is. We're given 2 volumes. Well, when we mix these volumes together, we come up with 50 milliliters of solution. And in order to calculate the mass, we calculate the total volume of the solution first, 50 milliliters, and multiply that by the density of the solution. And because we're assuming the density of water, our volume in milliliters will be the same numerical value in grams, and so the mass is equal to 50 grams. We then need to calculate our temperature change, and delta T is equal to the final temperature, 28.25 degrees Celsius, minus the initial temperature, 25 degrees Celsius. This gives us a value for delta T of 3.25 degrees Celsius. And when we multiply these numbers together, you'll see that we can cancel out units of grams and degrees Celsius. This gives us an answer of 680 joules. But we're looking for delta H in kilojoules per mole, so we need to convert joules to kilojoules. We know that there are 1,000 joules in every 1 kilojoule. This gives us a value of Q, or heat transferred, of 0.680 kilojoules. Now remember, we're looking for delta H in kilojoules per mole. And in order to find that value, we need to know how many moles we're working with. So our fourth step is to calculate the number of moles reacted in the reaction. And to do this, you can use either reactant. And that may sound weird at first, but I'll show you why as we go through our problem. I'm going to use NaOH. So I know that I have 25 milliliters of NaOH. And using the concept of molarity, and I also know the molarity of NaOH, so I could calculate the moles of NaOH using the molarity. But remember that molarity is equal to moles per liter, and right now my volume is in milliliters. So the first thing I need to do is to convert milliliters to liters. So 1 liter is equal to 1,000 milliliters. Once I have units of liters, I can use the molarity, which is 0.5. 0.5 molar means that there are 0.5 moles of NaOH in every 1 liter of NaOH. This allows me to cancel out units of liters. And this next step is why I could start with either NaOH or HCl. You see, we're looking for the delta H for the reaction. There's 1 mole of NaOH used per mole of reaction, so we're considering our entire written chemical equation as 1 mole of reaction. And in order to find the number of moles of reactants used in that reaction, you would just look at the coefficient in your balanced equation. This tells us that in this specific reaction, we reacted 0.0125 moles. Our last step is to calculate delta H for the reaction in kilojoules per mole, so we'll use each of the values that we just calculated. 0.680 kilojoules divided by 0.0125 moles. That gives us units of kilojoules per mole. This tells us that 54.4 kilojoules of heat are transferred per mole of reaction. We then need to assign a positive or negative sign based on whether the reaction is exo or endothermic. In this case, because the temperature of the surroundings is increasing and heat is being transferred from our system, which is our reaction, to the surroundings, which is the solution, and the temperature of the solution thus increased, that the reaction must be exothermic. And so we put a negative sign in front of our delta H value. And this tells us 54.4 kilojoules of heat are released per mole of reaction. You always need to assign a negative or positive sign if you're going to list the value as delta H. If you don't want to list the value as delta H, you could also state that 54.4 kilojoules of heat are released per mole of reaction, and that information would also tell you that the reaction is exothermic. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.